Hello and welcome to Topic 5, Cauchy's theorem and Cauchy's integral formula. In Topic 3 we looked at the differentiation of complex functions, and we're now going to turn to contour integration, namely the integration of complex functions in the complex plane. We're going to derive a few remarkable properties of contour integrals of analytic complex functions, namely Cauchy's theorem and Cauchy's integral formula. In this first video, we're going to look at integrals of multivariable real functions, and we'll see that in general, integrals of complex functions can be written as a complex sum of such real integrals. These are the intended learning outcomes for this video. After watching this video, you should be able to parameterize integration paths in the xy plane using a single variable. You should be able to express contour integrals as complex sums of real integrals. Along with this, you should have a picture of how complex integrals are an extension of real integrals, where now the function and the line element are complex valued. Lastly, you should be able to set upper bounds on the magnitude of contour integrals. And with that, let's begin.
Let's first talk about the integrals of real multivariable functions. Recall from our discussion in topic 3. We looked at real functions of more than one variable. And we defined such functions as doing something like this. You might have n real numbers as its input, and it returns a single real number as the output. And we also saw that for n equals 2, we can draw the function over the plane. As a reminder, I'll do a quick sketch. We give ourselves 3 axes, x, y, and f of x and y. And we draw the function as a surface above the xy plane. Might look something like this. And a point on that surface has a function value given by the height above the xy plane. And so this point would correspond to that on the y-axis and that on the x-axis. Back in topic 3, we saw how to define partial derivatives of such functions. If you'll recall, we treated x and y as independent variables. Now, what do multivariable integrals look like? We've done differentiation. What about integration? What do multivariable integrals, and we call these line integrals, look like? This is the setup we're going to consider. Given a path C in the xy plane, and we call that the line we're going to be integrating along, we can ask for the area under the graph of the function f along that line. Again, I'll draw a little picture. we have x, y, and our function f of x, y. We might be interested in the integral along a line in the xy plane that looks like this. This is our line C. The corresponding function value above that line might vary something like this. And we're going to want to calculate the area of this sheet that I'm going to consider for now is sliced up into lots of columns sticking out of the xy plane. And we can label a small distance along the line by delta s. This is our setup. A small change along the curve, and we've called this small change delta s, which is also called the line element. Well, this small change along the curve, delta s, is given by the corresponding changes in the x and y directions. By Pythagoras' theorem, we can spot that delta s is given by the square root of delta x squared plus delta y squared. We want to find the area of this sheet in blue. One way to do this is to parameterize the path C. So parameterize the path C with a new variable. Let's call it t, such that the path C starts at t equals 0 and ends at t equals 1. And why do we want to do this? Well, this means that we can describe the path C by its x-coordinate that depends on t and its y-coordinate that also depends on t. So we've gone from dealing with the variables x and y to dealing with a single variable t. We know that for small variations in x and y, we have that delta x is given by the derivative of x with respect to t times a small change in t, and similarly a small change in y is given by dy by dt times that small change, delta t. Using these expressions for delta x and delta y in terms of changes delta t, we can now rewrite our line element delta s as this. So it's going to be the square root, and then we've got dx by dt times delta t squared plus dy by dt delta t squared. This is all under the square root. We can take out the factors of delta t squared, and we're left with x primed of t squared. That's the derivative of x with respect to t. That's just shorthand. And we've then got y primed of t squared. These are both under the square root. And we take out delta t. To calculate the area of that sheet, we now sum up lots of terms given by the function value times the line element. Those are the strips, the blue strips on the diagram above. And when we take the continuum limit, this sum becomes an integral, and this is the line integral. Therefore, the line integral is given by, we write it as the integral along the path c of the function xy, and then in the continuum limit, the small element delta s is replaced by the differential ds. We said that we want to parameterize the path in terms of t. That means we can write this as the integral from t equals 0 to 1 of the function, now written in terms of t, and then times the line element, also in terms of t. This is an integral with respect to the variable t. That's how we do line integrals for real multivariable functions. Let's now consider something a bit more interesting. Let's now consider something that we're going to spend a lot of the rest of this course talking about, which is complex integration. Now we turn to integrals of complex functions. You'll recall from my earlier discussions that these map the complex plane to the complex plane. The analogy here is that now our axes are going to look like this, where we have the real part of z given by x, the imaginary part of z given by y, and our complex function f of z. And now when we're dealing with an integration contour in the complex plane, so the xy plane is now the complex plane, and now the complex function value corresponding to this path in the complex plane is going to be assigning a complex number to every point along that line. I'll write it as this line which is changing colour to highlight that the real and imaginary parts of the function will be changing in general. And we're now interested in the complex number corresponding to the area of this sheet. To reiterate, now we want to evaluate integrals like something like the integral along c of f of z dz, and these are called contour integrals. Here the path c is called the contour. In the complex plane. Looking down on the complex plane, we'll therefore have something like this, where, as in the diagram on the top right, we have the real and imaginary parts of z, and our contour might look something like this. This is c. We might go in this direction, and I've used this multicoloured pen to emphasize that there is a complex number associated with each point along this line, and so just as the function value is a complex number that changes along the line, so too is the line element along this contour in the complex plane. Similarly, as for real multivariable functions above, we could specify this contour parametrically. So we could say that down here t equals 0, and up here t equals 1. I'm going to write that down below. As for real multivariable functions above, we can specify the contour parametrically. That means now that x is a function of t, y is a function of t, and to define these, t lies between 0 and 1. We know that we can separate our complex function into real and imaginary components. In other words, we can write, and you'll remember this from topic 3, f of z is a real function u of x and y, and then plus I times v of x and y. V is another real function of x and y. You'll also recall that we can write changes in z in terms of the corresponding changes in x and y. And again, we can recast these in terms of t, and we get x primed, where this is understood as dx by dt, plus I y primed times dt. Now our contour integral looks like this. We had the integral along c of f of z dz, and this can now be written as an integral from t equals 0 to 1 of the function value, which is u plus iv, and then dz becomes x primed plus I y primed dt. Multiplying this out and separating real and imaginary parts, we then obtain this is the integral from t equals 0 to 1 of u x primed minus v y primed dt plus I times the integral from t equals 0 to 1 of v x primed plus u y primed dt. And you'll notice that both of the integrals that you have to calculate are real, and of the same form as the real multivariable integral earlier. It's only the factor of I that makes this whole number complex. This means we can say something pretty neat. In principle, we can always think of a complex integral as the complex sum of two real integrals. However, we will see that properties of complex functions can allow more elegant evaluation of such integrals. Similarly to our discussion of the triangle inequality in topic 1, we can bound the magnitude of complex integrals. Now suppose the integrand, our function f of z, satisfies this relation. So its magnitude, the magnitude of f of z on the contour C, is bounded from above by some real number f0. What does this mean we can say about the magnitude of our integral? Let's denote the length of the contour C by L. Then we have that the absolute value of our complex integral, we can rewrite this in terms of an integral with respect to the variable t. From above we have f is u plus iv, and then dz gives this. Applying the continuum limit of the triangle inequality allows us to write this as the integral from t equals 0 to 1 of the absolute value of u plus iv times the absolute value of x primed plus iy primed. And then because t is constrained to be between 0 and 1, it's a positive number, and so the absolute value gives us dt. We know that the complex function's magnitude is bounded by f0, and that means that we can replace the absolute value of u plus iv by the real number f0. This is now the integral between 0 and 1 of f0 times the absolute value of x primed plus iy primed dt. We can take f0 out the front, and the absolute value of x primed plus iy primed can be rewritten as the square root of dx by dt squared plus dy by dt squared. So that's the magnitude of a complex number, dt. We recognise this expression inside the integral as our line element from earlier. And we're left with f0 times the integral along the contour of the line element. And that returns f0 times the length of the contour, L. This is along the path C. The outcome of this is that if the modulus of the integrand is bounded above by the real number f0, then the modulus of the complex integral that we've written above is bounded above by f0 times L, where L is the length of the path of integration. A final point to end this video. We're often interested in contours that are closed. And what we mean by that is that they start and end at the same point. And the contour forms a closed loop. By convention, we usually assume that such closed loops are traversed anti-clockwise. That's the same direction we take for angles in the complex plane to increase. This means that normal direction of travel will result in an increase of the polar angle in the complex plane. That's just a bit of convention that will be useful in later discussions of integrals. That's the end of this first video of topic 5. As a quick recap, we looked at line integrals for real multivariable functions, and we introduced the idea of contour integrals in the complex plane. We looked at how we can think of these in terms of a complex sum of real integrals. In the rest of this course, we'll derive some really remarkable properties of contour integrals of complex functions. Thanks for listening, and next up is the second video of topic 5.